We're now going to look at systems of inequalities. And so what we want to do is we want to graph each one of these equations like there was an equal sign. If it was less than or greater than with no equal to part on it, we're going to make a dotted line when we graph it. If there's an equal to part of the inequality, it's going to be a solid line when we graph it. So let's look at the following system. Let's say that you have 2x minus y is less than or equal to 4, and 3x plus 2y is greater than or equal to -6. So looking at the equations, you should be able to tell what the general shape is. You should be able to tell that if you look at 2x minus y equals 4 or 3x plus 2y equals -6, that those are lines. Both of them have the equal to part of the inequality, and so it's going to be a solid line when we graph it. Then we'll determine where to shade in a moment. For me, I would prefer to put this in the form of y, some inequality mx plus b. So let's subtract 2x on both sides. If we do that, we get -y is less than or equal to -2x plus 4. Recall, dividing by a negative or multiplying by a negative has to switch our inequality sign. And so if we multiply everything through by -1, we have y is greater than or equal to 2x minus 4. Okay, so I know what my y-intercept is, and I know what my slope is. So looking at this, our y-intercept is at -4, and our slope is 2/1. Okay, so let's graph that line. And so we have a point at 0, -4. And if we rise 2, we're going to run over 1. Rise another 2, run over 1. And so we get this line in here. So now we want to determine where to shade. This says greater than or equal to. Y is greater than or equal to 2x minus 4. If you're not sure where to shade, then you can always do a test point. Choose a point not on the line. So for instance, 0, 0, that's not on the line. If we plugged it back into this inequality, would that be true? Is 0 greater than or equal to 2 times 0 minus 4? Is 0 greater than or equal to -4? And that's a true statement. And so shading in here, we're going to shade above the line. Because it's a system, our solution is what the shading regions have in common. And so I'm just going to put little arrows here telling me this is where I would shade. And so now let's look at the other inequality. So let's get y by itself. So we could, to do that, we could subtract 3x on both sides. We would get 2y is greater than or equal to -3x minus 6. Divide every term by 2, we get y is greater than or equal to -3/2 x minus 3. So from here, we know what our slope is. It's -3/2, and we know our y-intercept is -3. So let's graph that line. We have a y-intercept of -3. And then if we fall 3, we would run over 2. Or if we rose 3, we would run over 2 in the negative direction. And so we get this line in here. So again, you got to determine where to shade. Is it going to be above that line or below that line? Is greater than, so I know that it's going to be above. But again, if you don't know, then do a test point, a point not on the line. And so if we plugged in 0, 0, would that be a true statement? Is 0 greater than or equal to negative 3 halves times 0, 0 minus 3? Is 0 bigger than negative 3? It's true. So we're going to be shading in the direction of where the point 0, 0 is, above this line. The solution set, it's what they share in common. And so our solution set is going to be this upper V. So any point on the line up here and up here. And everything where they have the shaded region in common. So everything inside of this kind of V shape going on forever. So any point that you would choose that falls on the line up here or in between, and you plug that back into your system of inequalities, it would satisfy all those equations in there. Let's say that we wanted to find this point of intersection. If that's the case, then we're looking at this as if they were equal to each other. So we're looking at the system of equation 2x minus y is equal to 4 and 3x plus 2y equals negative 6. And so you can determine if you want to use the substitution method, the elimination method, or matrices. I notice if I multiply 2 times this first row and add it to the second, then that would clear my y's. So if I do 2 times every term on each side of the equation, the first equation, 2 times 2x is 4x, 2 times negative y is negative 2y, equals 2 times 4, which is 8. So summing these two equations right here, we get 7x is equal to 2. So x is equal to 2/7. So that's the x value of that point, 2/7. To find the y value of the point, we want to plug that value in for x and solve for y. We actually did some work over here where we had gotten y by itself. So we could plug it into this y is equal to 2x minus 4. So y is equal to 2 times x, which is 2/7 minus 4. I'm going to need a common denominator, which is going to be 7. So let's multiply that negative 4 by 7 over 7. We get y is equal to 4/7 minus 28/7, which is negative 24/7, which it's the same thing as negative 3 and 3/7. So this point of intersection, this is where x is 2/7 and y is negative 3 and 3/7. So sometimes when we're dealing with these, and you've dealt with these in the past with intermediate algebra, and we've dealt with, or even I just taught this in elementary algebra, but they were always lines. So they were linear inequalities, a system of linear inequalities. We can now do these with any type of inequality. So it might be a nonlinear inequality when we're dealing with this and solving for the solution. So let me pull another example. Okay, so the next example is x squared plus y squared is greater than or equal to 9. And we have x plus y is less than or equal to 3. Looking at x squared plus y squared is greater than or equal to 9. If I look just at x squared plus y squared equals 9, let's first graph that equation. So you should notice that this is a circle with a center at 0, 0 with a radius of 3. Okay, so let's graph that. It's a solid circle, not dotted when we graph it because it has the equal to part of the inequality. This is saying it's greater than or equal to 9. So this to me tells me it's outside of the circle. But again, if you're not sure where to shade, you can always do a test point, not on the equation that you just graphed. And so if we plug in 0, 0 in here, we should get a false statement because that is not where I'm shading. So 0 squared plus 0 squared, is that greater than or equal to 9? No, right, that's false. So I'm like, that's not true. Right, that's not true because, and that's not where I shaded. And 0 is not bigger than 9. Okay, so we shaded in the correct place. Now let's look at x plus y is less than or equal to 3. So this is the same thing as if I got y by itself. Y is less than or equal to negative x plus 3. So I know I have a y-intercept at, not where I just put it. I have a y-intercept at 3. And I have a slope of negative 1. So if I go down 1, I'm going to go over 1. Down 1, over 1. Down 1, over 1. So looking at this, it looks like by my graph that this is crossing, and I can show that algebraically at 0, 3, and 3, 0. This is less than or equal to, and so to me, sorry, things just shifted. Let me just pause as we get back up to things. What the heck? I'm sorry. Let me pause the recording. Okay, so y is less than or equal to negative x plus 3. And so that tells me I'm going to have to shade everything below. And so we want the region that they both share in common. So if we had really shaded, where are they overlapping in those colors? And so if I did that, that would be out here outside of the circle below that line. That would be our solution set. Again, we can find out where these equations intersect by looking at solving nonlinear system. So when is x squared plus y squared equal 9? And when is x plus y equal to 3? So multiple ways we can do this. Actually, let's do it. One way actually I see how to do it right now, besides looking at the graph, is let's plug in what y is. Another way to write y is negative x plus 3. So let's plug that in for y right here. And if we did that, so we would have x squared plus whatever y is, quantity squared, equals 9. And y we said was negative x plus 3. So let's distribute. So we have x squared plus, if I distribute it out, negative x plus 3 times negative x plus 3, we would have x squared. That would be a minus 6x plus a 9 is equal to 9. Quadratic equation. So we would set this equal to 0. And so let's subtract 9 on both sides. Our 9 is going to cancel. And at the same time, let's combine these like terms. 1x squared plus 1x squared is 2x squared minus 6x. 9's canceled equals 0. We can factor out a 2x from both of those terms. So this is when x equals 0 and when x is equal to 3. If we go back in here and we plug in 0, not for y, for x. We would get that 0 squared equals y squared plus 9. The thing is, that's not going to give me a correct solution. Because if I plug in 0, that would give me 0 squared plus y squared equals 9. And we would get then y is equal to plus or minus 3. But notice that there was only one of these solutions. If I go back in here, so if x equals 0 and y equals 3, we knew that this was one of the points, but x equals 0 and y equals -3 is not one of those points. And you can try it by plugging those back in, right? If I plug this into my second equation, that's not going to work. -3 is not equal to 3. And so this solution piece is in part. And we could see that by looking at the graph. And then if we plugged in 3, so it might be better because I see the same type of problem going to happen because of that square in there. So maybe plugging it into x plus y is equal to 3. So when x equals 3, 3 plus y equals 3, y equals 0. Which again, we knew that was a point there. When x was 3, y is 0. When x is 0, y was 3. And so we have those 2 points and we showed it by just solving that algebraically, 0, 3, and 3, 0. If it asked for the points of intersection, those are not the only solutions. But that would be a great test question because that is showing me a lot of different things that you know how to do in one problem. Okay, so our next system of equations, we have y plus x squared is less than or equal to 1, and y is greater than or equal to x squared minus 1. You should notice that those are both parabolas, and because it's the x part squared and not the y, that they're either going to be facing up or down. Let's get this form in the form y inequality. So that's already the case for the second inequality, but for the first inequality, let's subtract x squared. And so if we subtract x squared, we would get that y is less than or equal to -x squared plus 1. So you should know what that graph looks like with transformations of graphs. The negative in front of the x squared is a reflection across the x-axis. Our parabola is facing down, and that plus 1 is shifting it up 1 unit. And so we have this parabola shape in here. This is less than or equal to. So my guess is I'm shading inside of that parabola shape. But again, I can always test it with a point. So if I plugged in 0 and 0, 0 is less than or equal to 1. And this is true. So shading within here is correct. Okay, so let's graph the other equation. The other equation is x squared minus 1. So again, to me, this is a parabola facing up, but shifted down 1 unit. This is everything that is greater than or equal to. So to me, this would be, again, everything inside the parabola shape, but we can test it, right, with a 0.00 again. So is 0 bigger than or equal to 0 minus 1? Yeah, 0 is bigger than -1. And so shading inside. So our solution set is like this. And everything inside that. I could test to see where my intersections are, but I could see in that case that we had the points of intersection would have been -1, 0, and 1, 0.